Welcome all. First, thanks Elif for making the opening speech. I'm not really good at it. Is my voice okay? I have pretty quiet voice. You all can hear? Okay, I will try. Today we will do perturbation. Let me start with writing the time-dependent Schrödinger equation from last time, which is minus h bar square over 2m psi plus potential energy psi equals IH bar perturbation, which is 55 psi. And I will perturb the field with defining a potential energy. Our system will be consider an atom, right? This position, well, it doesn't have a well-defined position, but somewhere around here, and we will have plain light waves like this propagating in this direction, and let's consider them polarized in the z direction, whatever direction. Let's say here is z direction. So in this field, in all points, electric field points in the z direction, and it's uniform, so all the electric field components are equal to each other. In all points, electric field vector is the same. And now I will describe electric field vector with, light is just the electromagnetic wave, so it will oscillate, let's say cosine omega t. Let me show that nu. This is angular frequency, and we will call this frequency the light field frequency. Okay? And I will define the potential due to this external electric field, let's say VE, as E times the position cosine omega t. I mean, it's just in general like this. You take the path integral. So our potential energy in this system will be V0, which is the internal electrostatic field of the atom. It's coming from internal energy, which is of no interest actually, and also the potential energy from the light field. First, I will consider the situation where we have unperturbed atom. So let's say this A is very smaller than V0. So simply V equals V0, I say. Then we will have some solutions to this time-dependent Schrödinger equation, which will be psi k, where k is any integer value. Schrödinger calls these proper functions. You may hear them as also eigenfunctions. And we will have, corresponding to this proper function, a proper value, which will be h bar omega k. I can also write this as h nu k, which will be the frequency of the k state. Also, I will use a property, the completeness of the wave function, and state that if I write this kind of summation, the linear combination of all the proper functions, I can get the wave function itself even and better. Let's write this with respect to depending on both position and time. So what's different I'm doing here than Schrödinger does? He puts here plus instead of minus. In this case, Schrödinger equation becomes like this. But I don't like this form because that's why I decided to put the minus here and write it like this. Okay. So let me clarify that these CKs are arbitrary, complex constants. Okay, they have physical meanings, but we'll come to that. Let's name these equations. Let's say this is 26, and this is 25. It's not 25. I write 25 right now using putting this into the Schrödinger equation, which will be I just put it in place, and I am naming this 25th equation. What I'm going to do is substitute this solution, this wave function, in here to get, let me write it in this way. I make substitution and get ck with respect to its derivative with respect to time, psi k e to the minus I omega k t equals minus I h bar you can see that V0 is vanished here. It's because we know that minus h bar square over 2m we know this is true because in the first place we defined we substituted the wave function here, solving this equation. These terms appear in both sides, so we can just cancel them to make things easier. There's a fly here. So I'll just use orthonormality of psi functions. That means if I integrate them in all space, I'll get either 1 or 0 if they are equal to each other. If they are not equal to each other, it's 0. It's orthonormality. Multiplying both sides with psi l and then taking the integral, we will get CL dot e to the minus I omega LT equals minus I h bar a. By the way, in the paper you may not see these equations in this form because I like to use some notations. I prefer to use some notations to the others that Schrödinger prefers. So that's why. So from last time, we defined actually what AKL is. We use AKK prime, but it's the same. Simply, E is the charge of the electron, psi k, psi l, z, dx, dy, dz. Since there is a z here, we can't use this one. Okay. Now what I'm going to do is to write cosine omega t in the I don't like calling these exponentials, but Schrödinger does, so I will. In the exponential form, e to the I omega t plus e to the minus I omega t over 2. I just write this in place of cosine omega t to get this pretty important equation actually. We will use this one both in the radiation, where frequency of the light field is low, and also the phenomenon where the light field is equal to or very close to the resonance radiation, which is the radiation frequency of this spontaneous emission. Okay, let me call this 28 prime. So all these equations, all the steps was to get this one. Okay. As I said to you, using this one, now we will examine the theory of radiation and dispersion. But in a specific case where nu k minus nu l plus and minus nu is greater than akl ck over h. Or in place of this one, I can write h bar. Then I need to convert all these to angular frequencies. So it's not very important. The physical interpretation of this is important actually. This one is any spontaneous emission frequency. That means if I have an electron in the K state and it goes to the L state, it will emit a photon with the frequency Vk minus Vl. It's just that. And we claim that, actually we accept in the first place that take the light field, let's call it incident frequency or frequency of the light field. The difference between them will be very small, independent of if nu k is greater than Vl, nu L, or the opposite. In here I can actually remind the physical meaning of AKL. The last time we have written for the unperturbed atom the electric dipole moment, which was minus k minus sigma k ck square a k k minus 2 all the k and k primes, they are different from each other, ck prime a k k prime, cosine is multiplied with this one, cosine 2 pi, or writing 2 pi is too ugly. I use omega k minus omega k prime t plus some different psi, just a phase difference, any phase. So in here, the interpretation will be if only the psi k and psi k prime are excited, then, and with equal strength, 1 over square root 2, k prime plus 1 over square root 2. This is simply the amplitude of the dipole moment corresponding to these two states. So this is the physical meaning. It's not crucial, even it's not important for the continuing arguments, but I wanted to remind. So by continuing with this proposal, we can say that, actually, let me plot this one. By considering only this one, we can say that this part here is small, right? Sorry, this is large, the opposite. And the coefficient will be small. So we will have kind of a function like this, very close to 0, and rapidly oscillating. If it wasn't like that, you're going to get this kind of function. So this will tell us one oscillation cycle is short and oscillation amplitude is small, so change in CL is small. So for one cycle, we can assume CL and CK to be constant. I will show that they are constant by putting a 0 on top of them. Now I will integrate this equation and integrate 28 to get, let me look, CL 0 over to H bar.
Az önce sağda çizdiğin plot neye göre plotu?
Plot, it's with respect to time, yes.
What with respect to time?
Since this is small, the change in CI is small, so for one cycle we'll take them as constants, which is here. So we have an expression for CL now. Using this, I will get the solution of the else states of the solution to the Schrödinger equation in our system, which will be, this is the solution, this is the else solution. This is just given, the definition. So what we are going to get, I'm simply multiplying this one with this part, okay? So let me spend some time, not much, a little, to explain the meaning here, the behavior in the else states. So this one is actually the excitation in the else state itself. So it has nothing to do with what we are aiming to do actually. If this one was 0 in the first place, we had no excitation in the else state. But if we have, then this just describes the wave function in the else state. But in presence of light fields, we will have this part, which will help us actually construct a secondary wavelet. This secondary wavelet is will cause some phenomenon called refraction. When light is present in matter, any material, let's say an atom actually, will produce a secondary wavelet which will interfere with the incident wave, which will create the refraction effect. So we are trying to get to that point. In this part, we will have a lot of oscillations actually. If we have excitations in many states, this is, you can think of this as the amplitude indicate state. If we have excitation in many states, then we will have in the L state a lot of different, a lot of oscillations with different frequencies, which will be nu k minus nu L plus nu, and nu k minus nu L minus nu. This is summation over k. So for all the k states, Schrödinger calls these vibrations in k states honored vibrations, because in honor of these states, L states has an oscillation with frequencies like these ones. But until this point, we don't get any physically meaningful expression for testing them experimentally. Before going there, let us consider this equation with the system where we have only one free vibration. That means our Ck constant will be 1. So in the beginning we will have an excitation only in the k state, and any other state will be 0 because it's one free vibration. Then just let me direct the right wave function for this system using this one and this one, which will give us at point 30. Now we will get a physically meaningful parameter, which will be electric dipole moment in the z direction. Normally, we can include in the electric dipole moment in the x direction and y direction for anisotropic atoms, but for now.
Before you go on, in the summation L, L is different than K, or can it affect itself? I mean, does it include the term L as well? I mean, when you sum, for example, if you have the state L or state K, when you're summing up, do you also include the itself in the summation?
One moment.
I mean, if you have one free vibration, then the summation is 0.
So what I did here is I believe it is contained in here, but figuring it out will take a bit much time for me. I feel it. So let me leave it to the end. Okay. Okay, then I'll just write the electric dipole moment, which is defined this conjugate z dx dy dz, which is going to give us this definition is still the same. Did I write it somewhere? Okay, let me continue. So what we are going to get from here is pretty important physically. Cat stole my show. In the beginning of the system, we had the electric field E. And I would think of like this electric field is brought here because of a dipole moment. I'm just thinking of this in abstract terms. Okay. If you have this equation, then we will have a number 2 pi z a, which will be this term will be increase in the refractive index of the body. And Z here is the number of atoms in a unit volume, which makes sense. Actually, in here, we obtained this value A. Like, where was this equation? Like this one. I said this part is not much of importance, but this one is for the secondary wavelets. It's the same here. This one is due to the excitation of the Kate state itself. It doesn't have anything to do with the light field, but this part does. Okay, and since since in the first place we said E equals the magnitude of electric field is A cosine omega t, then A will simply be 2 over h bar summation for all L's, omega L minus omega k, AKL square, comma, minus omega k square minus omega square. Or you can just turn this to H instead of H bar and turn all these to frequencies instead of angular frequencies. So actually in here we showed that the theory of Schrödinger agrees with the classical arguments. We obtained the value of A, which is correct. The interpretation of this parameter A will be, first of all, this denominator. This will be related with anomalous dispersion, which we will not pursue. Okay, it's just dispersion neighboring the desired frequency, let me say. Also, in here we explained, actually corrected again, Thomas and Kuhn's hypothesis. Which states that sum of all the coefficients in the dispersion formula, which are these actually, will be equal to E square over 4 pi square m. By working out Schrödinger's equations, I don't mean Schrödinger's equation, all these equations, we can also conclude to that point. So, theory is correct, it shows. One more thing. We explained here the system with one free vibration. But as stated before, there are secondary radiations with frequency other than nu. In here we have frequency, we have an oscillation only with frequency nu, right? This is omega, so the frequency is nu. In order to get that, we need to have more than one vibration in the atom. More than one state should be excited. And the oscillations will be in frequencies nu plus and minus, nu k minus nu k prime. Since we had no difference in our states, we had only oscillation with frequency nu. So I will move on to the resonance radiation. Which means that incident radiation frequency is equal to or very close to natural emission frequency. For it, we will consider one case where nu k minus nu L plus nu is small, and frequency in the L state is greater than the frequency in the K state, so higher energy. That means if this is small, in the exponential, it will cause appreciable changes to CI. If this is small, then we won't have small cycles like this, but cycles that take longer time. So this will cause appreciable changes. So appreciable, we will omit all the other terms, actually. I will continue with, where is it? This is the most important equation, it is 28 prime. From there, as I said, I will omit the terms that are not causing enough change in CL. Instead of, we will write CL dot. I'm rewriting equation 28 prime actually. Will be, there are some substitutions here, I will show them. Don't panic. So, in here we will have substitutions. Sigma is A over 2h bar, A KL, and epsilon is minus omega k minus omega L minus omega. By working out these equations, I will reach to a point where I get intensities for CL and CK, which will be intensity of these ones, which I did not show the substitution to, but I will. There's a pretty significant interpretation here, but before that, let me write substitutions, where x is CL e to the minus I epsilon t over 2, y is ck times e to the I epsilon t over 2, mu is gamma plus epsilon over 2, sigma, and gamma is also defined in terms of these. We will have theta. Theta is defined gamma t plus phi prime over 2. What are left are phi prime, rho, and rho prime, which are actually arbitrary real constants, and possibly non-negative. Let me erase this part. I can't erase this one. Maybe I can. So one thing, and something that is expected, is some of the intensities is a constant. What is here is not of importance now, but yes, it is constant. So if we have a frequency of light field that is very close to the emission frequency of Kate and L states, the summation of intensities of these states will be constant. Now I will choose a certain time, okay, so that cosine theta will be 0, because I want all the intensity to be on Ck. For it, I impose directly cosine theta is 0 and rho prime equals rho over mu. Okay. Then we get for mu rho prime. This is the part of the intensity that oscillates, and that is the one, the constant one. So I want to find the fraction of the intensity that is oscillating. So this is the oscillating intensity, and I write the intensity of Ck here, Ck square. That is, or I don't want to. That is 4 mu rho prime over mu rho plus rho prime square equals 4 over mu plus 1 over mu square equals so I will do something here. Gamma square can be shown as just taking square here, epsilon square over 4 plus sigma square. That will lead to gamma plus epsilon over 2 over sigma equals sigma over gamma minus epsilon over 2, which is mu. So I will plug in these values here and obtain, okay, I'm directly writing sigma square over gamma square, which is sigma square over sigma square plus epsilon square over 4. Interpretation here will be when we have epsilon equals 0. What does it mean? Epsilon equals 0. That means Vk minus Vl plus omega equals 0. So frequency of the light field is equal to the spontaneous emission. That is Vl, yes, Vl minus Vk. Vl is greater. If we don't have a perfect resonance, we will have some fraction of the intensity that is oscillating. Also, there is a physical interpretation of sigma that is a correspondence to the natural sharpness of the resonance line. So it's in the emission spectrum, it just shows how sharp our lines are. However, we don't have a unit system for it because there is no universal agreement idea on the amplitude A, the amplitude of the electric field. There's no universal agreement. So this is the end. Thank you.
So, does gamma also have significance like that?
Let's see. Well, it's not that obvious as I see. I don't know if it's. Let's see. If it's equal to sigma, epsilon is 0. It's simple to think of epsilon, I guess. Questions?
I don't know if it's very simple, but what is resonance radiation? I don't get it.
It is when our light field, the frequency of the present light, nu, is very close to emission frequency. That is, when an electron goes from L state to K state, it radiates a photon with this frequency. If frequency of the light field is very close to that one, you'll have resonance radiation.
Why could we omit some of the terms?
Because, like before, this part was large delta. In the beginning, we used that one to say that CL should be constant then. This time they are so insignificant, we just omitted them. Okay, we can end, I guess.